All right, good morning. Good morning. You guys are all asleep in here. I know it's a cold, yucky, gray, horrible. Everybody should sleep in until noonday, right? Yeah, we can't do that. I wish we could, but we need to find out some things. So, we talked about the other day, what are the three structures we're going to have? The only three we're going to have the entire class. Everything we do in this class from now to the end of the class is based on these three items. What are those? Yeah, sequence of selection and a loop. Everything we do is on that idea. If you can remember those three things, you can pass this class easily. That's all you have to do. It's three things. Three things. So we're going to look at those a little more in depth, and we're going to look at what we're talking about. We're going to introduce you to a couple of oddities about them. So remember, we can have our sequence, just a list of items. We can have our decision. And remember that decision can only be a yes or no or a binary decision. I can't ask a question that's got three possibilities, right? I have to do some work to get there. But we're going to show you how we can do that. So we can get around that the computer's really, really dumb. And then we have this thing called a loop. And I want to look at this loop really carefully. So in that little drawing of the loop, so our flow chart of a loop, that loop does something interesting. So it asks a question, and while that condition is true, so it's a while loop, while that condition is true, it executes a piece of whatever we have in there, and then goes up. And it goes only to the very top of that loop. That's the only place it can go to, is the very top of that decision. And that's going to become important here in just a second. So I want you to make sure you looked at that and you go, yep, that makes sense. It only can go to the top of that decision tree. So we know we can stack all these together. All right. And we know that sometimes we call them a little different name. So an if, then, else statement is our decision. We know that we can stack them together and we can just put them like blocks. Plug, 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 plug. And our loop down here, notice it has to come back and around to the beginning of that decision. So we're checking at the very top of that structure to see, does that condition exist again? We can also do what we call nesting. And so nesting says we're putting one structure inside of another one. Well, that doesn't look horrible yet. So we can put any structure in type of another structure. We talked about nesting and we started looking at this idea of a structured program. And remember, here's our three pieces. And so if I draw something on Word or I use PowerPoint or I go out and get Visio, these are my three structures. And I can literally plug and play and click those in like they're big Legos. So that's my three pieces right there. The problem we have is one strange little issue. And that strange little issue, and this is probably the weirdest thing we have, is if we have a program, and we're going to show you this, do not do this because this is wrong, but in this particular case, let's look at this program we've written here. So this one says, all right, we have our start and we have a stop, but where's that stop at? It's over on the right, a little odd place for it. And on that start, we say, all right, we have a square box. So we have some kind of computation, some kind of something processing why it's going on. And in this case, we're declaring a couple of variables. And that looks familiar, right? We had to declare variables last week. And here we say we're declaring a numeric variable called original number and one called calculated answer. Then we have a input. And that input says input original number. Well, we've declared it. We put an input in. Well, it doesn't look weird yet. And then we ask this particular question. And so this is very common to do. Instead of having to write out what we're doing, we just write end of file. And end of file tells us we've written something in there So if you type 999 or 0, whatever it is we set it up as a sentinel value, we're going to end the program. And we use these decision trees to do that all the time. So that makes sense in our brain. If I just say EOF or end of file, that means we've got some way that we escape out. So if you type in 999 for that number, boom, it exits the program. If you type in any other number, it says, all right, your calculated answer equals original number times 2. And notice that the variable we're putting the data into is on the left of that equation. And then we output calculated answer. And then our loop says, oh, we're going to go back up to the top of that input. So what is different about this than what I just said we had to be careful of when we're doing loops? It should go correctly. It should go right up here at the top of that. We can't put another statement up ahead of that and loop into that. There's a whole lot of reasons why, but for now, let's just pretend that, it's a magical rule and we can't do it. So what we can do, though, is change it a little bit. And so notice what I've done. I changed this. So this is essentially that same program, but changed just slightly. And so now we get our declarations, our input. It comes down into this decision. That decision controls that while loop. So while we're not in the file, we can make our loop. And so it says calculated answer, output calculated answer, and comes back up to the top of that loop. Well, we actually made it a structured program now. We didn't violate any of our structured rules. It's plugged in. There's a sequence, and then there is a loop, and they're plugged in together. But what's the problem with this? So if you run it through in your brain, I get a number, I come down here, what's going to happen to this program? So follow it through with numbers if you want to. So we declare those values. So they're zeros right now, we hope, right? Input original number. Somebody tell me a number. 2, 1, 23, doesn't matter. Let's go with 23, just because I like 23. I don't know why. So our original number is 23. Our end of file, we were going to use 999 or something to put out there, okay? So it's not 999, so we're going to go in here, and we're going to make original number times 2. So 23 times 2 hopefully is 46, and that gets shoved into calculated answer. Our output then says output calculated answer, so we output 46, and our program comes back up here and asks into file again. So the number that's asking, so we put in 23, so it's saying 23. Is that our end of file? No. So it comes back here, it multiplies it by 2, and outputs 46 again. And it continues to do that forever. So we have a little problem with this one, right? This is what we call an endless loop. In this particular case, if you don't put in a number that's going to end, this is just going to spit out 46 on your screen until you decide to turn off the computer, right? Does that make sense why it's doing that? So once we get a value for original number, is there any way for it to change? No. And we use it. This kind of answers your question about if we use a number over and over again. Because that original number is still hanging around at 23 and keeps going through this loop over and over and over again. So what we need to do is something slightly different. And this seems kind of odd when you first look at it. So this is called a priming input. So any time we have a loop, we have a priming input. So, any of you been out on a farm where you had one of those little hand pump wells? Everybody ever seen those? You guys are like, yeah, sort of. And you had to actually dump a little water down first to get it to start? You remember if you haven't had to do that? So, the reality is it's called priming the pump. So most of those old pumps, you actually had to put enough water in there to make that start to pump. So it's kind of an oddity. And so we've kept that. And so now this is our same program, but done correctly. So we have our sequence up here. So we have a declarations and we have an input. This input is what we are going to call our priming input. We have our end of file. So let's say they put in our 23 again. 23 goes in. We know that's not equal to 999, so it's not going to stop that program. And it comes into our loop. So calculated answer. So original number times 2, or 46, gets shoved into calculated answer. We output calculated answer. But now inside of that loop, we ask for a number again. So now it pops up and says, hey, would you like to put in another number? And so we could put in 2. And so now 2 comes up here and around. Is 2 equal to 999? No. So it multiplies it by 2, outputs that number, and asks for it again. So anytime we have a loop, we almost always have this priming input, and then we have an input inside of that loop. If I don't have an input or something inside of this loop that can change, then I can get stuck in that loop. It can run forever. So we have to have a priming input, and we have to have a way to change that value inside of that loop. That is one of the biggest problems I see, is we forget to put either that priming input, or we don't put in that change inside of that loop. And we don't want those things to run forever, so those 2 steps are important. So this, you're going to see this for the rest of eternity probably. At least it'll feel like that 15 weeks from now. So why do we like this idea of structure? So what is about structure that makes our life easier? What is it about it? The biggest piece about this is that bottom one there called modularity. So if we're structured, we can break things into what we call modules. And those modules, we can just start connecting them together. So if you take Legos and you put 10 Legos together in little blocks of 10 Legos, you can start stacking those even quicker, right? And if you have a plan for what you're going to do, you could have an entire group of people, each one of you assembling modules. The reality is, those kinds of things about being able to create modules make programming possible. It is hard for one person to write a very large program in a very time-efficient manner. Think about something like Microsoft Windows. Do you think one person wrote all of Microsoft Windows? No. It's that ability to put them into those modules that I think is really important. So that leads to that idea of efficiency, ease of maintenance. We're trying to all be very similar. So you'll see coding standards if you're at a company, and they will have standards about how things are done. And it allows you to write programs very, very quickly. So that's one of the big advantages with that. So there are some examples of structured and unstructured in here in your book, and you'll see them in this PowerPoint. So, for example, this, notice it just looks weird. There's something odd about that. So, what might be unstructured in there? So we have a decision. We ask a yes or no question. That part looks okay. And then it leads down to another decision. But notice how they're not completely separate. So we're going to try to write some and look at some of these. So there's a lot of examples in there. So here we go, taking an unstructured piece, and then go step by step in how to make it structured. This is probably the hardest thing. So notice now, I'm going to go all the way to the bottom. Notice how they're not tied together. This is a module. I can take it out. If I take this out, I snap it out, does that change my outside piece? No. And so that's what I want to look at. Is the easiest way when I look at code and I go, is it structured or unstructured, is can I snap out that module and then just draw a line straight down? These really are pieces we want to pull out in one little piece. So this is a really great example you'll find in your book, the online text. And this is the idea of a dog washing process. Most of you have had pets. Washing a dog is pretty tough, right? Has anybody had experiences with washing a dog that went badly wrong? Yeah. So, we know that cats are easier, right? You know how you wash a cat? Oh, I forgot Bailey's in here. So yes, some of them are self-washing, but the other way you can do it, in your bathroom you have a cat washer. If you just throw them in the toilet and flush it a couple times and flip them right out, they're good to go. And you have a freshly clean toilet. I'm kidding. We have 4 cats at our house. Love cats. They're great. They will save you in the house fire. But we have a dog washing process. And so this is an example of a process that we all understand and know. But we want to see if we can write it both as a, here we have a flow chart, and here we have some structured pseudocode. So we know very quickly we have a start and a stop on both sides. So the first process we do, before we can do anything, we have to catch the dog. First step. I used to have a little wire-haired rat terrier, and this was the hardest part, because she could sense as soon as you were going to give her a bath, she's off like a shot. So we have to catch the dog. We then ask a question, and we start a loop. And so notice that catch dog is actually the priming input into a loop right there. See that? So does the dog run away? If yes, well, we catch the dog and we keep repeating that loop until we've caught the dog. Maybe this takes 1 time, maybe it takes 100 times. Doesn't matter, because we've got our priming input and we've got our catch the dog. So notice those are 2 identical items. Does the dog run away? Well, now the dog's finally tired and the dog doesn't run away. So we turn on the water. Well, that turn on the water, now all of a sudden the dog goes, what? What's going on? I'm going to panic. And so we have to go back through our loop. It's the exact same code, except now we're adding some extra pieces in there. So does the dog run away? If he doesn't run away, so let's say this dog is really well behaved, we get the dog wet and apply shampoo. Does the dog run away again? No. We rinse the dog and we're done. But if the dog does run away, we have to turn off the water, catch the dog, and we repeat that little cycle there. And notice that's a modular piece of code. It's the same piece of code that we used earlier. Same down here. The reality is we reuse our own stuff a lot. And so if I look at that structure, the pseudocode, notice it's really a copy and paste, isn't it? So catch dog, while dog runs away, catch the dog. Does that make sense in our code? So while the dog is running away, we have to keep repeating that loop. So this is a really good example of a small activity that is a structured code. And structured code is what we would like to do. Because once I do that, notice no matter how many times we have to go catch that dog, do I have a whole lot of extraneous code in there for that? No. While dog runs away, catch the dog. I have to start out with that priming input of catching the dog. So those 3 lines happen over and over and over again in that program. This is the only class I'm going to tell you that copy and paste is your friend. Copy and paste, once you figure out some of this structure, how long would it actually take you to write this program? So if you think about it, of the 20 or so lines in there, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4 or 12 of those are that same structure, right? That indenting is also our friend in here, because that indenting comes down here and tells us where they're at in this level. And so notice in our flowchart, and they've done it very neatly, and it's hard for us without a lot of specialized tools to do it, but you can do it. Notice indent level 1, indent level 2, indent level 3. even on the structured code. So your guys' task today, and for this assignment, is you have to write, get back to the assignment, is you guys have some choices. Come on, Blackboard. Come back to me. So, we have a couple of choices. So you're really writing a structured flowchart describing the steps a retail store employee, a rock, paper, scissors, or the game show Deal or No Deal. So you have some choices in there. So do we have another game we can think of that might be a good example for us to try here in class? What else could we do that's similar to that we could examine here in class? Tic-tac-toe is possible, probably a little more complicated than what we'd like. Go fish might be a good example we can do, because we know that we do some of the same iterations again. It's been a long time since I played Go Fish. Any other ideas? Price is Right. One of the games in Price is Right might be a good thing we could look at. Wheel of Fortune, the Game of War. So there's a lot of different games that we can look at. So maybe we look at a section of, I kind of like the Price is Right. It's a great game show, been around for a while. Let's pick a sub-game, and maybe this game involves them guessing the right price on an item. We'll figure out something. All right, so before we do anything else, let me see if I can draw on my tablet so we can get it, hopefully, let it log back in. Reconnect. Why is it not connecting? I like to do the flowchart first to construct those. Why is my Deseri not working? I am at 10.20.208.1. Aha, there we go. All right, so what I'm going to do is blow up a text on like Notepad. And that way I have a blank screen that we can draw on here. So hang on just a second. So hopefully you guys can see this. We'll see if we succeed anyway. So we're going to do something about Price is Right. And so let's think about what kind of a game it is. Maybe it's as simple as they have to guess over or under a certain price. So let's say the price they have to guess is draw $2,300. Drawing crazy. Draw tool. Goes on. Blah, 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 blah. Then hang on a second. Let's see if I can figure out why we're not drawing here. Cool. Well, that's going to frustrate me. Yeah. Wow, I don't know why it's not deciding to work today. That will make my life a little more miserable. All right, so we'll draw it out a little differently. I'll have to grab a PowerPoint or something that's got some symbols, and we'll do something very similar, but it won't be apparently as quick. Yeah, they all do, actually. PowerPoint, Word all have drawing tools. So let's grab one of those, since apparently Desiri and I are not going to cooperate today. Don't save. Alright, so design, insert. Alright, so there are tools very similar inside of here, so we can actually do shapes, and we can do something very similar. So what I want to do is we know that the question becomes, I need to ask, is the price over a certain value? So I know I'm going to have a decision, and actually there's flowchart symbols right down here. So what's my decision symbol? So I have a sequence, so I'm going to drag one of those and insert it. Somewhere in here is my oval. Why are you not drawing? Shapes. My little oval connector. There we go. Close enough. So I'll have a start. Yeah. Alright, so we have our start. And that should be more oval. I didn't grab the right one. But insert my shapes. There we have our input-output symbol. And so now if I have these up here, I can copy and paste them in, which is kind of an interesting way to do it. Insert shape. And I want a decision of some sort. Come on, click. So, it's not quite the diamond I want, which was in there somewhere. Insert shapes. Where is the diamond at? Third one. Ah, there we go. All right. Why are you not grabbing them? Clunk. Clunk. All right, so now I have some basic shapes I want to use. What I can do now is copy and paste them into place here. So we know we're going to have our start stop, and I'm actually going to ignore that for now, just because I want to look at some of these pieces and get as much as we can here on the screen where you guys can see what we're doing. So the decision is, so Bob Barker is now long retired, but he used to ask clients, what is the price on that item? So up here on top, I'm just going to put some information I know. So we have Bob. We have our client or player. We know that it's a car with a value of, let's go, $22,000. They win this car by guessing the correct number. All right, so very simple piece on here. And maybe they have to be within $100. We could add all kinds of other things. But in this case, they win this car by guessing the exact right number. All right, so I have my symbols up here. And so the first piece I'm going to do is I know that I'm always going to have a priming input and an input inside of a loop, right? So I know I'm going to have two of these symbols. So I've already got a couple of them created. We know we have our decision. So inside that decision is price correct. Now I need to make that a little bigger so you can see it. But so is price correct? Ahead of this decision, we have to get an input of some sort. And so I'm going to put an input above there. And we may have another piece of comment, code, text, whatever. It says, welcome to the game show, whatever. So this actually asks, ask user price. So you're going to ask that player the price of this game. So we're going to have two sides to this. So you're going to have a, if the price is correct, yes. If the price is correct, no. So maybe in this case, they can keep guessing on that game. So let's actually make this, instead of just a decision, let's make that a loop. So inside of here then, I'm going to just copy this whole thing, and I'm going to paste it down here for now and kind of show you where we're going to go. So if price is correct, no. All right, so this is going to be our yes side over here. And so over here, I'm going to put this block. I'm going to drag him down. And that's going to be you win car. So here's a section of it. So now we need to do a little bit of artistry here with some lines. And so that same design and layout insert area, so we can now put in some lines if we want to. So there's all these handy connector lines, so I can go from here to here. And I can show we're going that direction. And now I want to go, similarly, I want to go from here. Oops, I want to drag that. I want to put in a line. So I'm going to put a line from here. Put in another line. So this, quite honestly, takes the longest time, is putting in our lines and drawing it out, which is why I wanted to use the tool, but that doesn't work today. Do what? I'm just adding in lines because they're snap to lines. There's probably easier ways to do it. I don't normally use Word for much, honestly. So you in the car. And then we have our end symbol down here. So one more line. And we have an end. So this actually says ask user for price. So it's really the same thing as what we have over here. So we're asking them, is price correct? And then this would be a yes, this would be a no. We're asking the user the price. So where does this actually go from here? Does it go straight down like I just drew? Or what's going to happen with that? Because right now, it shows that either whether they win the car or they ask the user a price again, the program exits. Where does this really need to go after they ask that user a price? Okay, so it really should go over here, back up, and it's always got to go back in at the very top of this loop. So this, let me edit that one out. This is really our only exit right at this point. So in this case, that user, in this particular case, how many times can they ask that price of that car and offer a value? So let's think through the logic. Is there anything to stop them from asking this price 10,000 times? So we ask the user for a price initially. Is the price correct? If they get it right, they win the car and they exit out of the program. But over here, we just keep asking that price over and over and over again. So is there something we could add or somehow modify this? Because right now, they could just start at 1 and keep going up by $1 every time, and they would eventually win the car, right? So you would have to set a cap of there in there. Okay. So in that case, we're going to change that loop a little bit, right? We're still asking this question, is price correct, you in the car, or ask the user. So in that particular case, what we actually are going to do is we're going to write a second loop around this one. second loop around this. This becomes that module. So this becomes a module inside of another loop. So we're going to have another loop so we're going to put in another piece here. And we're going to create a loop around this. So this becomes a piece of another loop. So you're nesting your loops together. Because you're nesting that outside that says, all right, we have 3 times to do it. That's a loop, right? And we can do that with another Sentinel value. So let's see if we can do this, if I have enough white space here to do this. So ask user the price. We know that that comes in to this particular piece. And we want to repeat this. How many times should we let them do that? 2, 3, whatever number we decide to pick. Can we write a loop to do something 2 or 3 times? Sure. Sure. So we're going to come up here to the top of this. And so we're going to create one that's based on a Sentinel value. So I'm going to just copy this real quick. Copy, paste. So, I don't want that one. Copy. Paste. Well, all right. Not sure why it's not copying the right one. Oh, that's going to irritate me. I'll just grab a new one before I decide to lose my mind. All right, so we're going to grab a shape. We're going to grab our decision. We're going to put a decision up here. And so that decision then, that decision really is an EO file, EOF. And we can pick whatever number we want. So as long as we don't reach into file, or if you want to be specific about it, let's try turn. So while turn is less than 3. So while turn is less than 3, we're going to come down and we're going to run this loop again. Let me see if I can connect those a little bit. So while turn is less than 3, we're going to go down. So this is that yes side of that loop. So yes. So I'll hold it there. I'll put it in a text box. I don't want to do it. So while this is yes, we're going to go through and execute this entire loop. While it's no, when that is no longer true, we're going to actually exit completely out of this loop. So we're going to go from here, we're going to draw around. This is why I was not an art student. And we're going to go around that loop, and we're going to end at this point right down here. So, and these would actually then connect. So now we've made a structured piece. So that ends. I could pull this loop out, and it's not going to actually change anything in our program. We won't ask the questions, but the program would still execute. So this one would work. Now, here's the question. Anywhere in here, am I changing this value for turn? So up above, I'm going to have a shape for, so I'm going to say turn is equal to 3. So now I've set a value for that turn. And I say, well, turn is less than 3. So is 3 less than 3? Is that true or false? It's 3, so it's false. So that would actually end. But here's the problem. So we have this value for turn, and we set it originally to 3 or 2 or whatever value we want to set it to. Do we ever change it anywhere in this loop? No. And so we actually need another one right up here. We would put it, so at the beginning of this, it would decrease that by 1 every time. So we're going to decrease by 1 our value for turn. So that way we know that every time we go through there, we have 3, 2, 1, bang, we're out. So if we write this as a code, a piece of code, so very similar type of structure. So we have a start, we have a stop, and then we know everything else is inside of there, right? So we have our declaration. So declare variables. And so we know we need to have a value for turn. We need to have a value for, we can call it guess. So that's a numeric. That's probably a numeric. And you could add in all kinds of other pieces, but we're going to try to do this as quickly as possible. So we're actually creating a while loop. So the outside while loop, so while turn is less than 3. So this next block of code, everything that's indented is going to run while this condition is true. And if I have a while, I need also an end while. So whatever's inside of this block, indented inside of there, is going to run while turn is less than 3. So we know it's going to run several times. We need to do a couple of things inside of there. You're going to ask a question. So the first thing you're going to ask is, you're going to say input guess. And then we're creating another loop inside of there. While guess so we really need another variable here called correct. So while guess is not correct, while that loop is running, so you can nest these as deep as you want to, and it gets kind of ugly sometimes, and that's why we do this indenting. So while that guess is correct, we're going to commit some kind of an action in here. So that's our inside loop. So this while is this outside loop. This while is this inside loop here asking the price. So this loop controls number of turns. This would be what we call our priming input. And this is our inside loop to check value of guess. So up here, we declared that correct, and we could actually just assign it a value. And we said 22,000. So they got a good entry-level little Corolla or something at that price. So while our guess is not correct, we're going to run what's in here. As soon as they guess correct, if they get that chance, this loop exits out, right? All right, so we're going to write the inside to this really quickly. So now we're indented again, because everything inside that while loop, we're indenting. So we've got a guess. So if, and you could write it this way, or there's a lot of different ways you could write it. So if guess is equal to correct, you could end the game right there. Well, we know that we're going to have them ask that question again. So inside of that loop, we know that they've got a control. So if guess does not equal correct, and you'll see we do a lot of that not correct, and so greater than or less than symbols, there's also some other depending on your language. I just use that to show that we're not correct. If guess not correct, now notice this, we're going to actually indent another piece, and we're going to say input guess, because we have to do that, right? This is our priming input. This is our input inside of there. So we can input another guess, and then that loop ends. Else, so that else really says, hey, you've won the prize, right? Because this says you're not correct, so this automatically would mean you're correct, right? So we're going to use another variable on that side, and we're going to say prize, and we're going to assign it the value of car, or correct, or whatever it is you want to put in there. Prize equals correct. So only if they guess the right price do we get any value for prize. And I'm going to show you it's a 0 up here. And so now we have this loop that's going to run, and hopefully it's going to only run 3 times. But we're missing one little piece in here. What are we missing in here? So let's think about what happens. We start this game. So while turn is less than 3, all right, we know turn starts out at 0, right? So we can even say it's equal to 0. So is 0 less than 3? So it's going to run this as it says, hey, what's your guess on the price of the car? All right, you guessed $2,000. Is $2,000 different than $22,000? So it's going to say guess again. And you're going to input a guess. If you had guessed $22,000 correctly the first time, it's going to assign a value to prize, and it's going to exit out of the loop. Because it's going to go, oh, nope, you're right. So in here, we have a couple of oddities. So this is going to run, but I run all the way through that loop and I come back up here to the top again. What's a problem that I'm seeing? Do I ever change the value of turn? No. So maybe the first thing I really need in here, and notice I left a line, is I'm going to say turn equals turn plus 1. So that way, every time this loop runs, it adds a value to 1. So in theory, the first time it runs, it's 0 less than 3, right? So that's loop 1. Loop 2, it becomes 1. Is 1 less than 3? We loop again, it becomes 2. Is 2 less than 3? It loops again, it says, oh, now we're at 3. Is 3 less than 3? No, and it exits out. So that part seems like it works if we put in this. So we're changing that sentinel value. If we didn't, it would keep running this whole thing forever and ever and ever and ever and ever, right? So here's what's also kind of weird. So notice in here, it asks for your guess, and then it gives you a second chance to put in a guess, right? down here. Do I need that second guess? Or do I need this guess in here? Maybe I need to move that priming input outside. If I do that, I'm unstructured. Because then I've taken those two loops and I've overlapped them. So think your way through these kinds of things and let's see what we need to do. So here's my input for this loop here. So at the end of this, let's just figure out that it made its way through. This loop ends. At the end of that loop, you could output so that prize then, that output, if you never guess the right price, what's that going to output? Hey, you just won 0, right? If you did win the prize, what's it going to output? It's going to output, because here we said prize is equal to correct. So we've taken a value from correct and shoved it into prize, and it's going to say you won $22,000. So, thinking about these games, they get hard to do all these pieces. It really is a little more complicated. That's why we do this in small stages, and we start thinking about like a very small game, and we start thinking about how you can do that. On your flowcharting code, you want to have one beginning and one end. If you have multiple exits out, you're not structured. It's got to have multiple exits out. So there are some flowcharting tools that are better than this. Obviously, I was going to try to use a slightly different model and just hand draw it. Sketch those out first before you even try to draw them. Quite frankly, drawing them out is probably the quickest, best way to do it. We used to sell, many, many years ago, they would actually sell little templates. But we can all draw diamonds and squares and ovals to show our start and our stops. Practice them. Try to come up with it. And then work your way through what's happening in there. Put in a value and work your way through. It's called desk auditing. So we can take a very simple example. So take something like this and work your way through. Or work a smaller structure and work your way through. And say, all right, here we have original number, calculated answer. We know those are equal to 0. Draw those up. Sketch it out. Put those numbers in a desk audit. And see if you can come up with something very similar. So this is a loop. This uses our priming input. So here is a very good value of a loop. You can use this as an example. And once you build one, you can take that entire structure and snap it in. You can say, all right, I know that I'm going to make changes. So in this one, we say end of file. That's what is the sentinel value is what we call it. So a while loop always has something that controls it. So while a condition is true, something has to occur. As soon as this doesn't work, we exit out of it, just like we did in our Wheel of Fortune. So you can take some structures like this and start modifying them for your own use. So here we have declarations. What if that input here was, instead of input original number, that input was input my guess? So end of file would be if my guess is correct, right? Calculated answer, you wouldn't necessarily need, but you can use very similar structures. So here we have a sequence. Here we have a sequence that's inside of a loop. And here we have our control structure for that loop. So this probably, when you looked at that assignment, you probably said, all right, that's pretty easy. I can do those. I can do rock, paper, scissors. But rock, paper, scissors has a little bit of an additional hurdle. What's the hurdle in rock, paper, scissors that will drive us crazy? The different outcomes. Because the reality is, it's not just a binary decision, is it? No. And so rock, paper, scissors means we have to nest a couple of statements together. And so I might have to nest, so if player has rock and you have paper, who's going to win? Yeah, so you got to go through that rule list, and you have to work your way through how that's going to work. It gets a little more complicated. Each of you have the ability to have 3 different choices, right? Each of you have 3 choices, so that leads to how many choices altogether? How many outcomes can there be in rock, paper, scissors? 6? How about 9? So you have 9 different outputs you have to deal with, or possible outputs in rock, paper, scissors. So if you think about it, you can draw those out. You can go rock, paper, rock, scissors, rock, rock, and then other outcomes then. So you need to figure out how those all happen and who's the winner. So in our brains take this in and think pretty simple how we solve that. But doing it in code gets a little harder. So we have to figure out those outcomes. So one way to do that might be some loops where you have possibilities. So you'd ask a question, is player 1 have rock? If not, does player have paper? If we know they're not rock or paper, we know they have to be what? Scissors. So you can use that statement. And later on, we'll show you some easier ways, hopefully, to break those out. But you really are going to take a set of questions to figure out that answer.
So
Yes, sir.
I have a question for that.
Okay.
So like for the flow chart, for like a loop for the rock, paper, scissors.
Okay.
You say like, are the choices the same as in, so above that I said like, you and a friend make a random choice between like rock, paper, scissors or whatever.
Okay.
And it goes into, our choice is the same, and then if it's yes, like the game is draw. And then before you would loop to play again because it was a draw, do I need that? What did you call it? Is it input?
The primary, so yeah, you'd have to have another input. But I like that. That's an interesting way to do it. You're kind of shortcutting and leading to where we're heading eventually. So that eliminates then.
I'm pretty sure I did it wrong, but now that we're talking about it.
That's part of doing this is we have practicing and looking at it. But that's a unique logical way to do it. So what Liam was talking about was rock, paper, scissors. His first question asks if player 1 and player 2's if their choices are the same, and shortcutting then to repeat the entire game because that's essentially what we do. So what you're really saying is you're making a fairly complicated statement, even though it sounds simple. So what you're really saying, let me just put this in here, is you're asking, is player 1 choice same as player 2? And so if you do that, then you're just creating a loop around the entire game or looping back up to it. And so that's actually an interesting way to do it. There are some other ways you can certainly do it, but that eliminates several of those inputs, and you can actually what you have to do is nest them all together and then one big loop at the end. But you could shortcut it with that kind of logic instead of having to do each one. So rock, paper, scissors seems like the easiest choice, and yet when you think about it, that game is actually really hard. So is the game of the one I used to make people do that was really hard to do was the game of war. And it sounds easy, but it takes some effort. So here's my advice. Draw this on paper first. Draw it out on paper. Use multiple sheets. It's great. Paper's cheap. Use those symbols and see if it makes sense. See if that logic, when you work through it, try to play the game or try to do the activity that you have in there and see if it works through there. It's called desk auditing. You're going to use that desk auditing skills all the way through here. When you write live code, when you write code, the pseudocode. But what we're trying to do is figure out how to break down some smaller, simple games and try to do that. So as you start thinking through like rock, paper, scissors, then think about, holy cow, how do I write that structure for a complicated game? So think of Call of Duty. They're doing the same type of thing. They're writing down these rules about how that's going to happen, and they're having to structure that code to fit that. All right, any questions? Anybody's head hurt right now? Don't wait until 10 o'clock on Sunday to start this. If you do, you're probably not going to get a good grade on this one. Ask questions, try. Yes?
You said draw them out. I know we're supposed to turn the assignment in online, but what if we turn the code in and bring them together from the drawing tool?
You can scan it and send it so it's in Blackboard. Word is not there are a lot of there's even some online tools that work. Word is what we have available. Almost everybody has. You can get a copy of SmartDraw and use it as a trial version, and it just puts. Yeah, SmartDraw works pretty well as one of those. It just has a watermark across it that says like trial version. You're welcome to use that. We used to have actually Visio in here in the lab. The problem with Visio has to do with how it installs versus the rest of Microsoft Office in our lab. And so I could either have Visio for this class, or we could have the entire Office suite for every other class. And apparently, I lost that battle. But you do have through our DreamSpark / Microsoft Imagine / now Azure connection, whatever they're going to call it, you do have Visio available if you want to download that. It's a full version. And it works really great for all kinds of drawing scenarios. But quite frankly, start with pen and paper or pencil and start drawing them out. We can all draw these symbols. It doesn't have to be perfect when you're drawing it out. And if you mess up, you crumple up the paper and you start over again really, really quickly. So that's why I was trying to use the drawing tool on the iPad that normally works, but clearly today is not going to be one of those days. So practice, try them, and then whatever you come up with, try running it through. Try playing that game through it. And you may go, oh, holy cow, I've created an issue. There's a loop where it'll play forever, or they get unlimited terms. So try that. And this is where it gets interesting, is we have to break down those structures of, in this case, a very simple game, but think about what we would do if we wanted to break down a business problem. It works very similar. So we're just trying to get in that mindset of how to break problems down into smaller and smaller pieces. This is like those word problems we always hated in math, but now you're trying to figure out how things work. All right? Any questions? Comments? Anybody hate life right now? No. If this is the worst assignment you're going to have all week, it's going to be a good week. All right, let's get out of here, guys.